Hi there. In this video, we'll be looking at different ways of reshaping tensor into PyTorch. In data science and deep learning, we may have come across this use case many a times. Like when LSTM layers, the input required is in a particular shape, and it can be mentioned using the batch first argument. As you can see, batch first by default it is false. So the batch dimension should be the second dimension. But if we want, we can give it as true, and then batch dimension will be the first one, which is usually the case. So whatever input we are having, we need to convert it into required dimensions, required order of dimensions, so that it can be fed to our LSTM network. Also for convolution neural network, the required shape is in the shape of number of batches, channels, height and width. Okay, so every layer has its own requirement of input, and whatever input we are having, we need to change the order of dimensions such that it meets the requirement. Also, while flattening the tensor, we use the reshape operation. Okay, so there are mainly four major operations in PyTorch which can be used: reshape, view, transpose, and permute. We'll look at them at one by one. Okay, so first let us create a tensor in PyTorch. Here I have created one tensor with 3 rows and 5 columns. Okay, first row is having 1, second row 2, and third row 3. The shape of tensor is 3, 5. We can look at this tensor as one batch of a sequence model where we have sequence length of 3 and each sequence is of dimension 5. Okay, so now let us suppose that we want to transpose this tensor, or what we want to do is that we want to bring the token dimension as the first one and the sequence length as the next dimension. Let us suppose this is the requirement. Okay, now let us use the reshape operation and see what happens. I have reshaped here the tensor a dot reshape 5 comma 3. So, and this is the output we have got. As you can see, this is not the output what we desire. Okay, here if we see that our data structure or structure of the data has been distorted, semantic meanings has not been preserved here. Okay, what I wanted actually was that this row of 1 should get transposed into the column of 1s. Okay, second row of 2 should get transposed into the column of 2, and likewise. Only I wanted was that dimension should get swapped or the order of dimension should change, but data itself should remain the same, or meaning of the data should be preserved. But here it is not the case. What actually happened here is that like in the memory, this tensor will be represented as the contiguous rows. Okay, so first row will be there, and then the next second row and third row. So from there only it has created this tensor of shape 5 comma 3, considering this tensor as a single row from the memory itself. Okay, so, or you can say that it has merged and split the array. Okay, and created this one. So to obtain the desired array, the tensor which we were looking at, we can use two operations: transpose and permute. We will first look at the transpose. Okay, so what transpose does is it takes 2 dimensions as input and then it swaps those 2 dimensions. Okay, so here since our tensor A is of 2 dimension only, so there are 2 dimensions 0 and 1, and we have given this as input, so it will swap those 2 dimensions. So first dimension is of size 3 and second of size 5, so it will swap and then our shape will become 5 comma 3. Okay. Similarly, the order of dimension here does not matter. Only it takes 2 dimension and then swap those. So even if we give transpose 1 comma 0, then output will remain same. Okay. So this is what transpose does. And we'll now look at permute. Permute is basically more generalized form of transpose where it can take n number of dimensions and input. Transpose can only take 2 dimensions, but permute can take any number of dimensions, and like it can perform any operation. Okay, suppose if we have nd tensor, then we can reorder those n dimensions in any format. Okay, with any combination or permutation. So for that, let us consider 3 dimension tensor. First, we will increase the dimension of our tensor A to 3. So we have used unsqueeze operation here. What unsqueeze does is at the given index, which is 0 here, it will add a dimension. Okay, so right now the shape of A is 3 comma 5. It will add a single dimension at the start, and the shape will become 1 comma 3 comma 5. Okay, so the size of B has now become 1 comma 3 comma 5. So size is 1 for the first dimension, because since we haven't added any new data, we have just created a dimension. Okay, so that dimension size to that dimension will be 1. Size for that dimension. Okay, now let us use the permute operation. So now our shape of B tensor, which we got after unsqueezing, is 135, and suppose we want a tensor output shape as 513. Okay, we want our second dimension here to be the first one, and first one to be the second, and so on. So in terms of indexing, we will first give it as dimension 2, which is 0, 1, 2, and then 0 and 1. So shape of C will become 5, 1 and 3. Okay, so as we can see 5, 1 and 3. So this is what transpose and permute are all about. Basically, wherever possible, we should use permute in place of transpose because this is more generalized operation, and transpose is only will only take 2 dimensions as input, so I have those 2 dimensions. But permute can work on any number of dimensions. Okay. Here, basically, we only change the order of dimensions for transpose and permute. No change is done to the data itself. Okay, right. Now we'll look at the view operation, view and reshape. Let us consider another tensor. Here, this tensor is of shape 2, 4. Okay, and we'll look at if this tensor is contiguous or not. So yes, it is contiguous, and we'll understand now what means by a tensor to be contiguous. Okay, so whenever array is created in PyTorch, is stored in memory such that rows are stored in contiguous memory location. Okay, so rows will be stored one after the other, and if that's the case, then array will be then that tensor will be contiguous tensor. Okay, so here we have first row 0, 1, 2, 3, and the next row 4, 5, 6, 7. So in memory, this array will be stored in this way. Okay, elements will be stored in this way. All right. So we can also see the stride of this tensor. Stride is 4, 1. What does a stride means is that given this memory and stride, we can obtain the tensor which we required in a given shape. So stride 4, by stride 4, 1, we means that from any element to go to the element in the next row, we in memory we will have to go to the fourth element. Like from 0 we can go to 4, fourth element 1 to 5, 2 to 6, and 3 to 7. So we'll from 1 will if we want to go to the element in the next row, then we'll have to go to fourth element. And 1 means from any element, if you want to go to the element in the same row but next column, then we will have to use a stride of 1. Okay, so basically what PyTorch does is it uses the tensor present in the memory and this stride to perform all of the operation for this particular tensor in our given shape. So using this stride, it can represent this memory into this form, into this shape. All right. And this is contiguous. This is contiguous since rows are stored contiguously, one after the other. Let us create the transpose of this tensor. Okay, A transpose is not there. And now what we have found out is this A transpose is not contiguous. Let us see why. What is A transpose? A transpose basically this transpose version of our A, and it comes out to be this 0, 4, 1, 5, 2, 6, 3, 7. But actually our tensor A in memory is stored like this. And we know that in order to be contiguous, rows should be stored continuously or sequentially. So 0, 4, 1, 5, 2, 6, 3, 7 should have been the representation if this A transpose was supposed to be contiguous. But since the representation is not like that, therefore A transpose is not contiguous. Okay, so we'll look at the stride. Stride for A transpose comes out to be 1, 4. Means if you want to go to the element in the next row, then we'll have to go to next element in the memory. Okay, from 0 to 1, from 4 to 5, likewise. And if you want to go to the element in the next column within the same row, then we'll have to use a stride of 4. From 0, if you go to the fourth element, then we'll reach to the element which is in the same row but the next column. Okay. Now we'll look at the data pointer, data pointer for both A transpose and A, and we find out that data pointer for both of them is same. So data pointer basically is the address of that location where this tensor is stored. Okay, so both A transpose and A points to the same memory location. It means they are both sharing the same memory, but actually by having different strides, they are forming the different representation. Okay, or they are having the different shapes. All right. Now we'll use the view operation. Okay. So here, if you can see, we have used view operation on A transpose to convert its shape to 2, 4. Presently, A transpose of shape 4, 2. All right. So as many of you have noticed or heard that view operation cannot be performed on non-contiguous tensor, reshape should be used in case of non-contiguous tensors. So here also we are seeing that PyTorch has given us one error. It says view size is not compatible. View size this which we want to make like 2, 4 is not compatible with the input tensor size and stride. At least one dimension spans across 2 contiguous subspaces. Use reshape instead. We will look at what it means later. Let us now use reshape and see what happens. Okay. So for the same operation, we are using reshape function now. So A transpose dot reshape 2, 4. So reshape was able to work fine, and we got our tensor B, and tensor B is like what we expected. So let us check it's contiguous or not. So it is contiguous. What does it mean? Let us check the data pointer also. So data pointer for B is different from data pointer of A. Okay, as you can see. So B was tensor which was formed from A transpose, but its data pointer is different. Okay, it means that B is not actually pointing to the same memory as A transpose or A, but it actually pointing to different memory location. It means that what reshape has done here is it has allocated a new memory, completely altogether new memory for B. It has created a new tensor. Okay, so B is basically not a view but a copy of tensor A transpose. Okay, so a point need to understand here is that the operation which you wanted to perform, view could not do that. View could not do because it was not possible to return a view from the given tensor of the required shape. And reshape also did exactly the same. It could not provide a view, but it has indeed created a completely new tensor for this the desired shape. All right. And since the new tensor has been created, so it is contiguous because the new location must have stored elements in the order in which B becomes contiguous. Okay, 0, 4, 1, 5, 2, 6, 3, 7. Okay. So let us now apply one more operation to the A transpose and see what happens. Okay, so here we are converting it into shape 2, 2, 2. And we have obtained a tensor C. So here if you see, then we were able to apply a view operation on a non-contiguous tensor, and the result is also non-contiguous. So how did this happen? Earlier we saw that we were not able to apply view operation on the A transpose, but here we are able to apply. Okay, let us see. So C dot data pointer, it is same as A transpose dot data pointer, means C is pointing to the same location as A transpose and A. Means C is sharing the memory with them, and here view has therefore view was able to perform the operation. Let us see what reshape does in this case. Okay, so A transpose dot reshape has given us a tensor, and data pointer, it is same as A and C. It means reshape has also given us a view of the tensor in this case. Reshape also hasn't created any new copy or allotted a new memory for this tensor D, but it has actually used the same memory location and provided us with a view in the required shape. So how did this happen? What was the reason? Okay, let us look at our tensor B, which was created by the copy of tensor A and then our original tensor A and C. So if we see the stride for the C tensor is 2, 1, 4, and it looks like this. So we'll just first see. Okay, so let us start with the first dimension. Okay, and the stride for the first dimension is 2. So from 0, if you want to go to the next element in the first dimension, it will be 2. Okay, the stride is 2, so we can go to the second element in the memory. Okay, so from 0 to 2 we can go, and from similarly from 4 to 6, 1 to 3, and 5 to 7. So within this memory location, within this memory allocated memory, we are able to reach to the next element in the first dimension, within the first dimension. And in the second dimension, the stride is 1. Okay, so 0 to 1, 4 to 5, 2 to 3, and 6 to 7. Within this memory we can do we can reach all the next elements. And for the last dimension, the stride is 4, so from 0 to 4, 1 to 5, 2 to 6, 3 to 7, that also can be reached using the same memory same memory representation. Okay, so like what we can say here is that from within this memory we were able to find a stride, particular stride, using which we can obtain a tensor in this shape. All right, but now let us look at the tensor B. Tensor B is here. So for like going from 0 to 2, 4 to 6, we need a stride of 2. Okay, so from 0, if we have a stride of 2, then we can reach to the element in the next row. From 4 also, from 1 and 3. Okay, so we can find a stride here, but if we want to go to the element in the next column, like from 0 to 4, we'll have a stride of 4. From 4 to 1, how will we go from 4 to 1 here in the, given this memory representation? We cannot go. Okay, we cannot. Like that's what the error was also saying. If you look at the error now, view size is not compatible with the input tensor size and stride. At least one dimension spans across two contiguous subspaces. So at least one dimension is spanning across two contiguous subspaces. All right. So it is spanning across two contiguous subspaces, and if we look at the documentation of view in PyTorch, so here also it says each new dimension must either be a subspace of an original dimension or only across a span across the original dimension. But as we can see here, it's not spanning across the original dimension, but it's going beyond that for tensor B. Okay, within if we see for tensor C, then given this stride and this memory, we were able to reach all the next elements given a starting element using the stride and this within this memory. But here for tensor B, we are not able to do so. Okay, so here for what we can say is that given this memory, We cannot find any particular stride which will allow us to use this same memory representation and obtain the tensor required which in this shape, in this particular shape, or the tensor required in this particular arrangement. So that's why view operation was not working, and reshape also gave us a completely new tensor, a completely new memory was allocated for this tensor. Okay. So three things here we understand here. First one is that transpose and reshape are different operations, and we should be mindful about how to use them and when to use what operation. Mostly, I would say that in most of the cases, permute operation is what we want, and reshaping only happens whenever we want to merge two dimensions or flatten our dimension. Mostly in those cases, reshape is used. And among reshape and view, um, if we are fully aware that yes, view operation can be performed, then we should use view. Otherwise, reshape is favorable in most of the cases, since it will work on all of the tensors for all operations. But wherever view will not work, it will just give us a new copy of the tensor. And the third point is, we cannot use reshape thinking that it will always give us a new copy of the tensor. Uh, no, it may give you a view also wherever possible. So, if you want an explicit copy of your original tensor, then you can create it by using the clone operation. Okay. So here we have created a new tensor by using c.clone, and even if you update the one element in the c tensor, then it won't affect our tensor, clone tensor. Okay. So here we have changed the c, first element of the c, but the clone tensor remains same. Okay. And if you are having gradients in your tensor c here, then you can detach it first and then clone. Okay. So explicit copy needs to be created if you want it. Otherwise, reshape will often give you the view of the tensor itself and will not create a new copy. So these 3 points I think we should keep in mind. That's all in this video. If you like the video, please like, and if you have any feedback, do comment. Okay. Thank you for watching the video.